Yeah, you should start at 3:35, 2 minutes.
Okay, sure.
I made you a co-host.
Yeah, I got that notification.
I think you can start, Diganta.
Okay. Yes. Is my screen visible?
It is visible.
Okay. Right. So it's basically I'll start with the alphabetic round lecture, and this will be sort of a lecture on uh, a, s- a tool which is sort of a representative of a wide class of tools known as AlphaBetaCrown. And I mean, it's a very interesting technique which also scales really, really well for at least certain classes of networks and certain classes of properties. And we will see what kind of networks and properties this scales well for and why it scales well for such things and so on and so forth. Uh, but I think before that, what we would need to do is we would look at the name, right? So this tool is called Alpha Beta Crown, and there's basically three parts to the name. There's some alpha, there's some beta, and there's some crown, right? And the way that I'm thinking of going about this is actually I'll start from the left. Uh, I'll talk about a technique that was proposed and named crown, which was simultaneously independently discovered by a separate set of authors, and these guys named them deep poly. So basically there were two groups of people, mainly one based on several universities in the US, mainly led by UIUC, who came up with the paper called Crown. And the same technique with very few differences was came up by Martin Vescher's group at ETH Zurich, which is called Deep Poly. So whenever I say deep poly, it's, you can interchange it freely with Crown, and Crown can be freely interchanged with deep poly, right? But these two teams, they develop the techniques in very different directions, and eventually the tool AlphaBetaCrown right now, I think, is mainly maintained by the US based group. So yes, it's a very interesting tool, and I think I'll just get on with it now. So sure.
Still, Deep Poly and AlphaBetaCrown, do they have existence independent of each other, or they are merged into AlphaBetaCrown?
Yeah, so deep poly exists so basically each of these tools went into integrated separate tools, right? So
Okay.
Crown was developed and finally integrated into AlphaBetaCrown. Deep poly did not really build itself up to a complete solver the way that Crown did, and I'll explain what I mean by complete solver and so on as we go forth. What happened with Deep Poly is that they integrated themselves into this tool called ERAN, which is purely an abstract interpretation tool from ETH Zurich. So this is the ETH robustness analyzer tool. And I think, they have some commercial versions of this available now as well.
By the way, I have not introduced anything about abstract interpretation.
Yeah, so I'll talk about abstract interpretation.
Term, okay?
Yeah. So I dropped a term there.
Of abstraction, over approximation and all those things that they have seen. But the term abstract interpretation has not been introduced. Just
I'll explain exactly what abstract interpretation is. So if that felt like a terminology drop, don't worry. Most of these slides will be sort of explaining what abstract interpretation is within the context of Crown and Deep Poly, right? Because these tools are kind of fundamentally based on abstract interpretation as a technique, right? Okay. So so let's begin there itself, need for over approximation abstraction, and finally motivation to go into abstract interpretation, right? So of course, the need for over approximation is something that I think as you would already understand from the perspective of this, that abstraction is something that is useful if you can implement it smartly. It can really accelerate solvers well, right? So the motivation for the structural abstraction in the node merging techniques was kind of to create something that will over approximate the behavior of the original network, right? So I have not talked about or not compared it with the node merging abstraction, but even ReluPlex itself has some amount of abstraction built in, right? So what does ReluPlex do? Just to recall, kind of, it is going to do this kind of a thing where it's going to assume that your ReLU constraints are it's going to basically just drop your ReLU constraints. So if you have a network that looks like something like this, then you got some linear layer and then ReLU constraints here, and then linear layer again, and then ReLU again, right? So it's going to drop these guys and just have these linear constraints and use an LP solver for that. If the LP solver gives you unsat with respect to whatever property, that means it's safe. Otherwise, it's going to try and reintroduce these constraints back in and see if we can get a violation. And then eventually it will have to do some kind of case splits, right? So it will have to split on whether this particular ReLU, is being fixed to the active phase or fixed to the inactive phase, right? And then the worst case scenario kind of for ReluPlex is that each of these cases will have to be analyzed separately. So that is kind of sorry, it's not absolutely not infinitely many, but it's kind of like an exponentially many case splits will need to be done, right? So this is the kind of crux of the ReluPlex algorithm. But the other thing is that if you let the Real algorithm run for a very, very long time, it'll always come up with an answer. It'll always tell you a yes or no answer. It's never going to be the case where it says that I don't know what's going to happen, because eventually it's either going to analyze all your possible cases and then say it's unsafe, or if before that it finds a case where there is a bug, it'll report that bug, or if somehow it's able to drop some ReLU constraints, and based on that, the abstract LP formulation already gives you unsat, then it's going to say that this is unsat itself, right? So this is it's always going to produce a yes or no answer, and this is something that we will contrast with some of the later algorithms, right? So, and the other interesting thing about ReLUplex to keep in mind as we go forward is that it always keeps very specific values of the variables around, right? So, I mean, if you stop the ReLUplex algorithm at any point, either within the LP phase or within any of the other phases, it is actually exploring a very particular specific value of the network, right? So let's say that we have stopped the ReLUplex algorithm in some phase, and let's say that this particular ReLU has been, these ReLU constraints have been dropped, then it is maintaining some values of these variables, some values of the forward versions of these variables on one side of the ReLU constraint. It is holding some values of these variables and then some values of these variables and so on, right? And these values are going to satisfy a partial set of the constraints. So it's like it's going to satisfy some of the linear constraints, some of the ReLU constraints has been dropped and so on, right? So it is carrying around these values of variables. If you were to pause the ReLUplex algorithm at any point and ask, okay, what is the value that the algorithm is looking at right now? That's a meaningful question to ask, because you can actually extract the values of this variable and say, oh, it's actually exploring this particular value. It's looking at this particular scenario, this particular case, right? So in some sense, it's kind of explicitly going through the space of all possible values. Of course, it cannot go through every possible values, and it does not need to. It's just utilizing the piecewise linearity to avoid doing that by making these LP calls. But it is kind of exploring the space of values explicitly, right? So if you were to imagine that your network is some piecewise linear kind of structure like this, and it's some piecewise linear mesh, let's say, with various pieces, right? What ReLUplex can be thought of as doing is it's starting here and then maybe exploding and going here and then maybe exploding and going here and so on. Right? So it's actually tracking some explicit values, input output values that can be seen in the network, right? So some of these values may not actually be there in the network because the ReLU constraints have been dropped, but nonetheless, these are explicit values, right? And so in that sense, it can also be said that it's carrying the entire information of the network. I mean, it might be dropping the fact that some variables are related by a ReLU constraint, but other than that, it is carrying the entire information. It's carrying the whole, set of possible relationships among all variables, right? So this is what the ReLUplex algorithm does, and it's not very surprising to you, I think, right now that this is not scale. I mean, we've seen this in the case of when we're looking at the node merging abstraction already, that this is not scale, right? And the key idea, I think, in getting this to scale is to say that we should be able to terminate before analyzing all possible cases. And this is, I think, this is actually, in my view, at least, a fundamental idea behind various different kinds of solvers, not just neural network verification solvers, but things like even SAT solvers and SMT solvers spend a lot of time in doing things like learning clauses and so on, where the goal is to be able to do this kind of early termination. It looks very different in various different cases, but the goal is always this, avoiding analyzing all possible cases. Can we stop and say something with some kind of a guarantee? Because, I mean, of course, a guess is no good in our domain, right? We want safety guarantees, but can we stop and say something with some kind of a guarantee before we have analyzed all possible cases, right? And yeah, so one, of course, way of doing it is by the node merging abstraction, right? So if you kind of merge some nodes and you have an abstract network, and with that abstract network, you are able to, if you can prove that abstract network is safe, then you have terminated before analyzing all possible cases in the concrete network, right? So that is one way of doing that. But that has, as we discussed in the experiments, it has got some downsides. It's very kind of it's finicky in the sense that it really is dependent on what nodes you choose to merge, how you choose to do the merges, and while there are potentially a lot of benefits in terms of it being solver agnostic and the networks being much smaller, and you can have the networks around for future analysis and so on, but it's finicky in that way that you really need to be careful about what you're merging and how you're merging, and it's not clear what choices there leads to good performance and so on, right? So of course that does terminate before analyzing all possible cases, but yeah, as we saw that it's perhaps and practically as well, it's not been the case that it has scaled up as much as the techniques that AlphaBetaCrown are based on have scaled up, and we'll see the reason why. But before going to that, I want to just go back to Reluplex and say that, okay, I mean, is there a situation where Reluplex will terminate before analyzing all possible cases? So, I mean, as I said, there's potentially, again, this is a typo, horrible typo. There's potentially exponentially many case splits, right? And of course, the worst case scenario, Reluplex will have to do exponentially many case splits. My question to you is, when if or when will Reluplex be able to terminate before having to go through all of these exponential case splits? What is the situation where the Reluplex algorithm as is going to be able to say that, oh, look, the network is safe before exploring all possible case splits? Any guesses?
When you ask when, you are asking
Right.
what kind of situations,
What kind of situations?
yeah.
Yes.
Anybody?
So more concretely, I'm not asking you to give me an example of a network and property pair. What I'm saying is that what kind of, I mean, if let's assume that the Reluplex algorithm terminates, then what must happen during the analysis? What must be true about the network so that that happens? Any guesses? Anybody? So I hope the Reluplex algorithm is something that you all recall, right?
Well, they should.
Okay. Yeah.
Let me give it. I don't know. Maybe you want to give a
Yeah.
hint, or let me give a hint since I
Sure.
since I lectured on Reluplex. Oh,
Yeah.
and
Yeah.
a hint is obviously if you didn't need to case split, what does the case split do? Anybody? What does the case split do when you have to do a case split on a Relu node? It splits it into active, not active, correct? So if you
Right.
didn't need to case split, what is it? What does it mean? Okay, that
Right.
is there must be some part of the answer in it. Now, anybody?
Maybe let me simplify the hint even further. What does the solver try before doing case split? So, of course, the solver is going to try active, inactive, right? And this is what's happening after its case split. But at this point itself, the solver is trying something, right? I mean, it doesn't immediately do a case split, right? So it tries something before doing a case split. What is it that it tries something that before doing a case split?
Checking if the variable is below the upper bound and up the like above the lower bound.
Right. Yes, that is true. But also, what does it do to the ReLU constraints? I mean, it does check whether the variable is below the upper bound or above the lower bound, and it adjusts them. But even before that, it does something to the ReLU constraints, right?
Variable before and after the release should be equal if in its active state and should be zero after if it's in inactive state.
Yeah, so that's how the network actually behaves, right? But the Reluplex algorithm doesn't do that, right? So what the Reluplex algorithm will do is that, so basically let me maybe give the answer. So what does the ReLPlex algorithm do? If you have a network and let's say that this is the ReLU constraint, right? It's going to create this sort of this is your ReLU. So of course, like you said, what the ReLU is supposed to do in an actual network is that if the variable has some value that is greater than or equal to 0, it's going to take this value of the variable and it's going to output the same value, right? So let's say that this is x before and x after, then in this case, x after should be equal to x before. Otherwise, x after should just be equal to 0, right? So this is what actually should happen. So if you have these set of constraints, then you're modeling the ReLU perfectly. But what ReLUplex will do is it will not take these initially, right? So what it will do is that instead it's going to say that, oh, I'm going to drop these constraints altogether, right? So it's going to completely ignore the relationship between x after and x before. So practically speaking, what it will do is, see, if you have a network where you have, let's say this is the linear layer, and these are some of these weights and so on, right? So you might have the variables coming after the ReLU from layer L-1 here, and then you have the variables coming going into the ReLU in layer L, and then you have ReLU constraints, and then you have the variables going after the ReLU in layer L and so on, right? So it's going to keep track of all the linear relationships between so these guys linearly related to these guys because of all the weights over here, right? So it's going to keep track of all of these linear relationships. So xbl xa l-1 times some matrix should be less than or equal to some value and so on, right? So it's going to keep this, but it's going to completely drop the relationship between these two things, right? So it's going to say that xal is not even related to xbl, right? So when this sort of a thing happens, when this relationship is completely dropped, and this relation only the actual linear layers are kept in place, that is when ReLUplex is going to do an LP call. So this is the sort of drop ReLU kind of abstraction, or drop ReLU kind of formulation that ReLUplex does, and then it's going to do an LP call. And if the LP says that it is safe, then we know that the network itself has to be safe, because if you drop the relationships between XAB and XLB and XLA, and still the network is safe, that means no matter what this ReLU layer would have done, the network is safe. So in particular, if this ReLU layer is actually doing this, the network is safe, right? But if it says otherwise, then we don't know. So then we need to somehow add some ReLU constraints back in, and then we'll have to do the split.
Yeah, that is true, but I want to interject here.
Right.
But when ReLUplex terminates, before it completes it, of course, it has a step of where after the LP call, it tries to see which ReLU pairs are broken, and it tries to fix them such that all of them are, it fixes them all. Okay, and if it is able to fix them all, and then a further LP call, in a consistent way, and which then it stops. Correct?
So yes. So that is the other situation, right?
Yeah. So
when it will be able to terminate early. So yeah, maybe let me give the full kind of picture here. So it's instead of just going into the split and add back in, let's say that it's going to do some ReLU fixing. And again, if this is going to give you an actual counter example, right? So now see, if it fixes and it gets something that is consistent, then that means what? This is a counter example, right? So then it's going to stop and output this counter example. Otherwise, it will have to do some splitting and adding back the ReLU constraints, and then again, repeat this loop, right? So is this okay? So if we are to avoid doing splits as much as possible, then we should aim to kind of, when we say that we want to terminate early, we should aim to either exit via this route or exit via this route as early as possible, right? Now, of course, if you are exiting via this route, that means that the network is inherently unsafe and we are finding a bug. So in that case, sure, exiting via this route makes sense. But let's assume that the network is safe. Let's look at the scenario when the network is safe, which means that this will never happen, right? So if the network is safe, you'll never be able to fix ReLUs in a way where you find this. So in that scenario, this kind of an exit never happens, right? So then the only way to terminate early is to exit via this route. And the only way to do that is if when you're dropping the ReLU constraints, the network is still safe. Which means that in your neural network, no matter what you do, no matter what this ReLU layer does, the network should still be safe, right? So ReLUplex will really exit early only if your network is such that no matter what happens with your ReLU layer, no matter what your activation function does, the network is still safe, right? So if the activation function takes your variable and completely, like takes the input value and completely jumbles it up and outputs it, even then the network should be safe. Only then is ReLUplex able to conclude early on that the network is indeed safe, right? If you think about it, that's a very unlikely possibility, right? It's not something that is actually very likely, right? So we should not really expect this to happen very often in real life, and in fact, it doesn't really happen very often, right? So which is why ReLUplex, if you run it, it'll have to go through quite a number of splits before it's able to conclude anything, right? So yeah, so this is what I was getting at when I was asking these questions. I don't know if the question was fair, and I mean, I don't know if this makes sense. Any questions so far from the audience? Does this reasoning make sense? What I'm saying when I'm saying that this ReLUplex will not really ever terminate early, and we need a solver to terminate early if you want it to scale. So is this kind of motivation okay? Any questions? So whoever was talking about, it'll check if the variable is below the lower bound or above the upper bound. That sort of happens in the fixing stage, right? So that'll only matter. I mean, it'll do that, and it'll only matter if it takes this exit, and that'll only matter if the network is actually unsafe. But if the network is actually safe, then that is something that will not be the case, right? It's very unlikely that the network is safe. And even if you replace the ReLU activation function with some random function that jumbles up everything, it will still be safe, right? So that's very unlikely. So, I mean, but ReLUplex seems to only really will terminate in that scenario, right? So, yeah. Any questions? Okay. Sure. If there are no other questions, then
Yeah, I think you should go ahead.
right. Just yeah.
Please go ahead.
Yeah. So yeah. So basically, this is the kind of sorry, this is the second. Yeah. Anyway, let's just have the smooth scrolling. It's fine. Right. So what do we do, right? So we need some other kind of abstraction of approximation, right? So of course we saw node merging as one form of abstraction which will over approximate the network. But let's look at another way of doing it, right? So this particular style of over approximation is actually called abstract interpretation. And the idea behind it is that we are going to track sets of variables or sets of values of variables, right? So instead of saying sets of variables, maybe it's better to say sets of values, right? So if you remember, what was one of the key things about the ReLUplex algorithms was that it was tracking very specific values, right? So if you have your network at any given point of time, it was holding a specific value for each node and so on and so forth, right? But instead, what we are going to do now is we are going to track sets of values. So let's say maybe ranges of values, right? So instead of arguing that, oh, okay, right now, here's the values of these variables. And yeah, so let's maybe do an LPI iteration and now we go there. And let's maybe now fix some of the ReLU constraints and now we go there and so on and so forth. Right? So instead of changing the values continuously, we're instead going to talk in terms of ranges of values, right? So we're going to say that, okay, we are going to have this many range of values. So we know that, okay, the variable here lies in, this particular set. The values of these variables can be in such and such set and so on. And we're going to attempt to argue in terms of these things, right? So that will fundamentally let us handle multiple cases simultaneously, right? So, hopefully we'll not even have to do too many case splits. That does not turn out to be the case. There's no free runs. This is an NP hard problem after all, but it should, at least in certain situations, allow us to handle multiple cases simultaneously and not carry the entire information, and thereby essentially terminate before analyzing all possible cases, right? So if you can somehow, handle multiple cases simultaneously by talking about ranges of variable values. So for example, if you're talking about ranges of values, some of these ranges might be in the active phase and some of these might be in the inactive phase for a particular value. And if you can get away with talking about ranges nicely, then you would not have to do a split on that particular value, right? So that is kind of the goal. But as we'll see, this can lead to situations where you have false negatives, right? So you think that there should be a counterexample when there is actually really no counterexample, right? And these false negatives will correspond to the spurious counterexamples that you may have seen during the ink deck based node merging based abstraction, right? So similar to that case, there will also be spurious counterexamples of false negatives here that we'll have to handle, right? And out of the box abstract interpretation doesn't really give you any good way of handling this. Most of the tools that use abstract interpretation are actually combine the abstract interpretation with a different technique called branch and bound, which we will talk about a bit maybe in the later lectures when we go into the full-fledged AlphaBetaCrown, right? So this is going to be the kind of the motivation that, can we talk about sets of values? Can we talk about, ranges of values, sets of values somehow efficiently so that we are able to handle multiple cases together, right? Okay, so let's see if we can do that. So before that, I would like to talk about this one idea that is also kind of critical to both Crown and Deep Poly. And this idea can be taken in other directions as well. So this is called this convex relaxation. So very interesting. So I think I've missed adding references here, but I'll put references when I upload the slides. But there is a very interesting paper called the Convex Relaxation Barrier for Neural Network Verification. And what they argue, they kind of argue in what ways this idea is critical. And this has been used in other solvers like Planet and NeuralSat, and used in various completely different class of techniques as well. But the key idea of this is that, see, what is a good set of constraints to replace ReLU with when we are dropping ReLU constraints, right? So again, if you go back to ReLUplex, when we're doing the drop ReLU, what are we saying, right? So let's say that we have this xi and xj. So let's say that, xi goes into a ReLU activation layer, and what the variable that comes out, let's call that xj, right? And what ReLUplex will do when it will drop ReLU is that it will say that, okay, xj is not related to xi, right? So xj can be star, right? So if you think about what that looks like pictorially, see, the original value, the concrete value of what would have happened in your when you apply your kind of ReLU looks like this, right? So this is what the ReLU actually behaves like. So the actual pairs of allowed values of xi and xj that your network will see really or concretely will all lie on this kind of a line, right?
A blue line.
The blue line, yeah. So the colors and all are visible for everyone, right?
Correct. It is there. I was just re-emphasizing. That's all.
Right.
It's
Yeah.
visible. Yeah.
Right. So when I'm saying xj is going to be anything, what I'm really saying is that, okay, look, xi, so xi can be anywhere over here, and xj can be really anywhere, right? So it can be anywhere in this whole region, right? So that would mean that what reluplex is doing, let's maybe use a different color. Let's maybe use light blue for what reluplex is doing, right? So what reluplex is doing is saying that, okay, when we are going to drop this constraint, the pair of values of xi and xj that we are going to analyze with, that we're going to let the network have, can be anything in this whole strip, right? So this kind of again clarifies as to why reluplex does not seem to, why we need to do a split, because it's very unlikely that that the network will actually be safe if you consider all the possible values of xi. Of course, if the network is safe for, so if the network somehow takes any value within this strip and is still safe, that means the original network is also safe, right? Because in particular, if the network would have taken values only in the blue line, it would have still been safe, right? So if you're able to argue that, okay, you can take any values in this strip and you're still safe, then of course you have a sound proof, sorry. But it's very unlikely, right? Because such a network, if you're taking any value here and you still safe, that means that if instead of ReLU having been this blue line, if it had been something like this kind of a line, or this kind of a line, or this kind of a line, see, all of these things will be covered within this light blue strip, right? So under reluplex, proving that this ReLU, this blue line is safe, is as easy as proving any of these things safe, which means that reluplex is not being going to be able to prove any of these things, right? So if the reluplex proof goes through without having to do any splits, that means that all of these potential activation functions would also have resulted in a safe network, which is kind of unlikely, right? I mean, it is unlikely that the network that we have that is actually safe is safe in spite of whatever your activation functions would have done, right? So that is highly unlikely. Okay, so then what can we do? Is there some other set of values of pairs of xij that we can consider that is not that entire strip, but is still not as complicated as the blue line? In particular, is there some set of values of xi and xj that we can consider that lets us get away with not having to do a case split, but it is not as bad as this light blue strip, right? So what can this set of values be? See, again, if you look at the reluplex like algorithms, what these algorithms are doing is eventually they're doing LP calls, right? Which means that if you want to be able to do LP calls, so if you want to be able to get away without having to do SK splits, ultimately the tool that we're going to use for analysis is doing an LP call, right? So instead of having the exact constraint, so this is the blue exact constraint, right? Instead of having this exact constraint that, okay, xj, so let me say this thing, right? So we have the exact constraint that xj is ReLU of xi, right? So this is not possible for LP to handle. We relaxed that to xj is star. This is possible for LP to handle, but it's too relaxed. So is there something in between these two things, right? So is there something here that is possible for LP to handle, but not as relaxed as just saying that xj is star, right? Is there something here of this nature? It turns out there is, and there is actually a minimal such thing. So you can have a set of constraints that you replace your ReLU with that is minimal up to the properties that LP should be able to handle it, and it should be a sound over approximation, and it should let you get away without doing a case split, right? So that is basically what this triangle approximation looks like. So see, if you want LP to be able to handle it, ultimately it needs to be a set of linear equations, right? So you need to somehow carve out the region in this space with a bunch of linear equations, right? And for it to be sound, you know that the set of linear equations that you want has to contain this blue line, right? So let's try to find the minimal set within this xi xj plane that can be carved out with just using linear inequalities, but also contains this blue line. What would that look like? Well, that would look like, see, it would essentially basically look like this triangle over here, right? So I mean, visually this must be clear. You can do formal proof by arguing that this triangle is indeed the convex hull of the set given by this blue line and so on and so forth. But I'm going to not go into that over here. It's not very difficult to show that this is indeed the minimal region that an LP solver will be able to handle, which means that it's carved out by inequalities and contains the blue lines, right? So this is basically this triangle, right? And then you can write that in terms of these equations, right? So you can say that xj is equal to some lambda times xi plus mu, but the exact values of lambda and mu will depend on where these lower and upper bounds end up lying and so on, right? And again, I'm not going to go into the exact values of lambda and mu, but you can imagine that you can calculate it based on the lower bounds li and ui, right? And also you'll have that xj should be, so xj should be less than equal to these things, xj should be greater than equal to xi, and xj should be greater than equal to 0, right? So these three constraints is going to carve out this particular triangle. And if you are using an LP based solver, so ultimately what you want to do is an LP call, then this is really the best you can do, because this you have to the only thing you can send to your LP solver is just a conjunction of linear inequalities, and you know that your conjunction needs to contain the blue line, which means that the tightest possible conjunction that you can have is going to look like this, right? So this is something, this is called the triangle approximation of the convex relaxation, and this is something that a lot of solvers, including AlphaBetaCrown, makes use of. But yeah, so one way to maybe go from ReLUplex to something smarter.
One thing
is
that I
to
want
say,
to add or comment here, or a question,
Yeah.
is of course you're assuming that you have an Li and Ui for Xi. Okay.
Right.
Yeah?
Right.
So
Right. Yeah.
once you have that, then this makes sense. I mean, correct?
Yeah, if you don't have an Li and Ui, this doesn't make sense. And I was kind of I mean, I was kind of not going into that right now, but you need these lower and upper bounds, right? Because if we don't know that xi is within this bounded range, then we won't be able to do this, right? Because then we won't be able to draw this upper line, right? So if you imagine that my blue line indeed does extend infinitely, that will kind of look like this kind of a situation, right? So let's say that this is my plane, and my blue line kind of extends infinitely in both directions, then there is really no upper bounding line that I can draw. Then I cannot actually, when I'm carving out this region, I can still draw this line, I can still draw this line, but I cannot draw any line like this, because then this part is going to get ignored. Even if I shift it upward, eventually there will be some part of the extended blue line here that is going to get ignored, right? So what your region ends up looking like is this whole space, right? So then it's no longer really a good approximation. I mean, it is still an approximation. You can still plug this in and build a solver around this and so on, but it will not be anywhere nearly as efficient. So you need these lower and upper bounds. And the question is, where do you get these lower and upper bounds from? And so we will sort of come to that. But let's say that somehow obtain these lower and upper bounds, and then you're using that analysis to now talk about or now to come up with this kind of this triangle region, and then use that to replace this ReLU constraint, right? So you can kind of do this. You know what ReLUplex was doing was that it would have started with this and replaced this. So this was the drop ReLU step for ReLUplex. Instead, what a lot of solvers do is that they start with this and kind of replace it with this, right? So instead of dropping ReLU, they over approximate the ReLU with this kind of a triangle region, and then use that to avoid doing case splits, and then use that to kind of then use the LP calls to kind of come up with a come up with a safety proof, and if the safety proof goes through, then you're done, right? But of course, this is not a panacea, right? Because I mean, we know that LP, for example, can be done in sub-exponential amount of time, which means that if this were to go through, you have solved. If this were always to work, we would have solved an NP hard problem in sub-exponential time, which is most likely not possible, right? So what can go wrong here? So what is the situation where this would not work? Is a question now that I have to use just to see if I'm making sense to all of it. How am I doing with respect to time?
No, you have.
Oh, okay. I've
You have half an hour today. Okay.
Yeah.
So were you asking
so
a question to?
Yeah, I'm asking a question to people. Like, okay, so I mean, we can do this, right? We can kind of do this triangle-based carving, and then replace every ReLU with constraints that look something like this, somehow using some lower and upper bound, right? So as Sir pointed out, I mean, the where do you get this lower and upper bound is a question, but let's say that somehow somebody has given you some lower and upper bound for each ReLU, and using that you've created this kind of constraints, and then now you're sending it to an LP solver, right? So you're sending it. So let's say that these are your ReLU constraints, right? So you're sending the LP solver an LP problem that looks like linear constraints for each layer, right? So for your whole network, right? So you'll have ReLU layers here, and then linear layers here, and so on, right? So you encode the linear layers into your LP formulation. You convert this ReLU into your convex relaxation, which is again just an LP problem. And then you take an AND of all of these things, and then you send it to an LP solver. And if the LP solver says safe, you're done, right? So my question is that will this algorithm work always, or is there a situation where, or okay, maybe let me ask this question. If now the LP solver says that this is not safe, if it comes up with a counter example, is this always going to be an actual counter example, or can this be a spurious counter example?
Anybody want venture a guess?
So thinking in terms of this spurious counter example, somewhat visually will become important later on as well, which is why I think it might be good to practice it a couple of times.
I guess the hint is that is it still an over approximation or not?
Yeah, is this somehow exact, or is it still an over approximation? Right. So just to repeat what I'm saying, so this is precisely what will happen, right? So you have, let's say, some network, right? So maybe, yeah, some network, let's say that looks something like this. These are your weights in your linear layer. And then I've got a couple of ReLU constraints, R for ReLU, let's say. And then I've got another layer over here. And finally some output, let's say, right? So something like this. This is again a linear layer, right? And what I'm doing is I'm now converting these guys into some equations, right? Converting these guys into the equations according to this triangle, right? So I'm converting this into 3 equations again according to the triangle. So these equations are basically just going to encode the weights, and similarly converting these guys into some equations encoding the weights again, right? And I'm going to take AND of all of these guys, and I'll have an LP problem which is sent to an LP solver. And let's say that now my LP solver gives me a counter example, right?
For
So
a
I'm
property,
asking
for some property that
for
is,
some property. Yeah.
yeah,
So let's say that my property is that this output needs to be greater than equal to 0 always, or something like that, right?
for
And
all values of the input. Yeah.
for all values of the input, and let's say that maybe I have some bounds on the values of the input, right? So you know, input is always between 0 and 1, and I'm encoding that into the equations as well. So so when I say equations, I mean inequalities. So we have the inputs being 0 and 1 being encoded into inequalities as well. The output being greater than equal to 0 encoded into inequalities as well. And when I'm taking the AND, I'm taking the AND of all of these things, right? And then I'm sending it to this whole thing to an LP solver. And the LP solver actually gives me a satisfying instance, which means it's a counter example, right? So so here I'll basically be encoding negation of these things. So let's say I'll say here y should be greater than equal to y should be greater than 0, less than 0, sorry, right? And I send this whole thing to the solver, and the solver actually gives me some values of variables along all of the network for which the input is actually between 0 and 1 and the output is actually negative, which means that it should be a violation of the property, right? So my question to you is, does that mean that the network is actually unsafe? Is this counterexample always going to be a true counterexample? Or is there a possibility that this counterexample is not going to be a true counterexample?
So let me pick somebody, okay, of the people who are still remaining in the class. Okay, I noticed that a couple of them dropped out. Lucky?
Okay.
Sir, I am thinking of an counterexample.
Okay, because you have not attended some of the classes where I covered over approximation and so on. So the key word is over approximation, okay? Whether it is modeling the original network precisely or not. Okay, Bijayan? Vardhan?
So don't think of an explicit counterexample. I mean, I've not given you what the weights are
Will
or
it,
what any of
I
this.
mean, will it always be a real count? I mean, will it be a real
Yeah, will it always
counterexample
be a real
or not?
counterexample?
That is the questions.
Yeah.
Paranika?
I'm still thinking, sir.
Yeah.
I'm not sure.
So, okay, let me see. What is the difference? Okay, let me ask it another way, if I may, Diganta. The class, I left Aritra out. Before I do that, I will ask the question. Why is these dashed lines, which is the set of linear constraints that is modeling this network, I mean, the original network, how is that, not accurate? Is it modeling it completely accurately, or the original network, or not?
No, sir.
Huh?
No, sir. Because of that triangle inequality.
Who answered this?
Sir, Lucky.
Lucky. Okay, so you're getting
Right.
Okay, so
yeah, absolutely, it's not right.
Yeah, so it's not, and therefore it will not be, because it is using an approximation. The entire region here is covered, whereas like what Diganta showed in the earlier slide, you only need to have this the dark blue, okay, whereas it is allowed these things. So therefore the answer is no. Yeah, for that reason, Lucky, that you did good. Yeah. Okay.
Yeah, so basically what can happen is, in some sense, your counterexample, let's say the xi xj values, pair of values in a counterexample can come from here, for example, right? So this will still satisfy the whole triangle. So it'll satisfy all of the inequalities that are part of this LP problem, but it is not on the blue line. So it's not something that can actually happen in the actual network. So yeah, so it can be that this counterexample is impossible in the actual network, right? Okay, so right. So yeah, I think now I didn't realize that this was right after, but maybe it would have been easier to show this on this example itself. So we're going to just keep using this working example, which is network kind of similar to the one I had drawn. And yeah, so we will use this in, so here, let's say that the inputs x1 and x2 are going to be between -1 and 1. And what we want to prove is that the output, which is x7, let's say, should be less than equal to 3, right? And as we keep going forward, we are going to introduce various concepts, and we're going to keep coming back to this network and using this as a working example, right? Okay. So now let's come to abstract interpretation.
Yeah, but
right? So
Diganta,
if you remember, yeah.
Diganta, did you want to say anything about this example or just
No, it's just introducing the example and the property.
Yeah,
So
this one
that
is
we can,
actually it is preserves this property, correct? Yeah, yeah.
yeah, it's safe.
Okay, fine. Go ahead, please.
It's actually a safe example, and that's why, I mean, so that's going to let us demonstrate this spurious counter examples, basically, right? So whenever we try to do an analysis and things come out to be unsafe, you know that something has sort of gone wrong, and your analysis is somehow not strong enough.
yeah, it's 4:30 now. You have 15 more minutes, 4:45.
Sure. Yeah, so I'll cover maybe abstract interpretation
much.
and
I mean,
interval
you
domain.
have 3.
Yeah.
I mean, see, the idea, I mean, I'm going to announce this for the rest of the class as well. We are spending, quite a bit of time in a more relaxed fashion, covering, we started with, after Z3, we started with ReLU-Plex, then node merging, which is both of which are part of the Marabou tool, and now Deep Poly and AlphaBetaCrown. Okay, these 3 tools you will have exercises to actually work on. Okay, and so you can expect some certainly some assignments in the next couple of weeks, which will ask which will query exercises, will query some questions on about the some of the concepts and principles behind that we have discussed behind these tools, and you will actually do some verification using these these tools. So Diganta, you can take three lectures, okay, on this. So please go ahead, and I'm just announcing it for the rest of the class to take these lectures about these tools seriously.
Right. Okay, so so if you remember, before we took this kind of short detour about convex relaxation, the motivation that we were or the direction that we were going on into was somehow to keep track of sets of variables, right? So the question then is, how do we keep track of sets of variables, right? So how do you actually carry around and argue in terms of sets of variables? So so if I have an equation that says that, okay, y is equal to x plus z, it's easy enough to take that and answer the question, what will happen if x is 0.5 and z is 0.2, right? We can just perform the calculation. But what does it even mean to say that, okay, what would happen if x is a set of such and such values and z is a set of such and such values? What is the set of values that y can have, right? So this is the kind of question, this is the kind of framework that we want to build, where each variable, instead of it having a specific value, it can have a set of values, right? So how do we do this, right? So the issue with sets is that they're infinite, right? So you can't really store a list in memory. So what is it that we can do, right? So what typically we do within formal methods based settings is that we use these things called abstract domains, right? So this is these abstract domains are kind of at the heart of abstract interpretation. And what abstract domains are is in some sense some parametric expression for a set of possible values, right? So I'll give an example. Intervals are an abstract domain, right? So for example, if I now say that my variable x, my variable x, instead of it having a value 0.5, I can say that it belongs to the interval 0.2 to 0.6, right? And then we can now somehow keep track of the beginning point and the end point of this interval, right? And by just keeping track of the beginning and end point of this interval, as we keep doing our calculations, we're essentially carrying forward a set of possible values for x, right? Similarly, we can have so we can
May I
have
suggest
intervals.
one thing, Diganta? Why
Yeah.
don't you have x is assignment statement, x is equal to x plus 1. Okay, after that, and then illustrate.
Right. Yeah.
Or maybe you do have, I mean, but I thought if you do have an example, that is good. No?
Yeah, I have an example
Okay,
bit
okay.
later on. Maybe.
Go ahead. Sorry. Yeah.
Yeah. So what I want to point out here is that, I mean, unlike, to keep track of this thing as an interval in memory, I mean, if you want to actually implement it, all you need to do is to keep track of the beginning and the end, right? So really, when you store this interval in memory in some kind of data structure, all that you need is the data structure to have this A and B as values, right? Similarly, you can have more complicated such parametric expressions. So you can have things like union of two intervals. So let's say that A comma B union C comma D and so on. And then you need to store 4 values in your data structure and so on, right? So now when we want to, let's say when we have an expression of this form or some other form like this, when we want to do calculation, so we're saying that, okay, X is belonging to this interval, Z is belonging to that interval. What is the interval that Y will belong to, right? So now all of our calculations need to not be in terms of just values, but be in terms of these intervals or be in terms of these unions of intervals or any other kind of structure that we come up with, right? So this is what abstract transformers will do, right? So it will take concrete operations and convert them to transformations on the abstract domain, right? So for example, if you had your plus, right? So plus was something that will take 2 values, right? So plus is typically what is a function that takes 2 values and gives out a value, right? But now we want it to operate on intervals, right? So now we need to have a version of plus that will take 2 intervals, right? So let's say 2 intervals and should give out again an interval as an output, right? So this version of the plus is called an abstract transformer for plus. And if you convert all the kind of concrete operations that you're interested in, let's say plus, multiplication, division, subtraction, into the corresponding abstract transformations, then you can take whatever expressions you were where you were dealing with actual values and just instead deal with these ranges of values like intervals and so on, right? And you'll have to do it for the particular abstract domain you're interested in. So if you're interested in intervals, then you have to do it for intervals. If you're interested in unions of intervals instead, then you have to instead have a version of plus that takes in union of interval, comma union of interval, and gives out union of interval, right? So you have to do things like this. So yeah, so I think so. I mean, this I'll just state, but I think it'll become more clear when I go to the example. These abstract transformers, what it will do is that it should be somehow sound, right? So when we're saying that it should take 2 intervals and give out an interval, it should really behave as if you're taking all possible pairs of values from the individual input intervals, adding them up, and then putting another interval around the output value, right? So in some sense, your abstract transformer should operate member and then choose the small representable thing. So now this is kind of abstract at this point, and I understand. So I'll go to the example, but understand that there are various choices of abstract domains and transformers, and there are various efficiency and approximation trade-offs involved, right? So yeah. So without further ado, let's maybe go into some examples, right? So let's talk about this particular kind of abstract domain called the interval domain. So let's say in this interval domain, the set of values is represented as a comma b, right? And what we are going to do is, to actually implement this, we're not going to store. We are going to store basically just a and b in memory, right? So you're going to have some data structures which is going to have just these 2 things like the pair, right? And when we have multiple variables, we'll have a Cartesian product. So if you have, let's say, 2 variables x comma y, right? So we can say something like x comma y belongs to AB cross CD, right? Which means that x is in the interval AB and y is in the interval CD, right? And yeah, so this is very fast to operate in, right? So let's see how we can do these kinds of operations. So let's say that we have, sorry. Yeah, so let's say that we have x is within this interval -1, 1. So what is 2x plus 3 going to be? So 2x plus 3 is an expression that looks something like this, right? So 2x plus 3 says that, okay, take x multiplied with 2, so we get 2x, and then, so this is star 2, and then you add 3, and then you get 2x plus 3, right? So let's say what will happen when we do this, right? So when we want to multiply it with 2, what happens to the concrete value is that 2 gets multiplied to it. So instead, when we want to multiply it with 2 in the abstract domain, we have to convert this multiplication with 2 into an abstract transform, right? So let's say that we know that x belongs to some interval a comma b, and we want to see what happens when we multiply x with 2, right? So now x is going to have a value between a comma b. So it can have any value that is greater than a and less than b. When you multiply it with 2, that will result in some value that is going to be between 2a and 2b, right? Which means that after multiplying with 2, the value that you will get is now going to be inside this interval, right? So if x is between a and b, we want to multiply with 2, the result is going to be between 2a and 2b. So this much is, I hope that clear to everyone, right? So similarly, if you add 3, it's going to be between so now let's say that I have 2a and 2b here. So it's now going to be 2a plus 3 and 2b plus 3, right? So if x was between 1 and -1, 2x plus 3 is going to end up being between 1 and 5, right? So now here's a question for the class. Can someone argue why when x is between 1 and -1, value of x will be between 0 and 1? Is this correct? Can someone argue why it's correct or why it's wrong?
Negative values, it will be giving 0. So for -1 to 0,
Who's answering this? Can you identify yourself?
yeah, I'm auditor.
Huh?
Auditor.
Retro. Okay, go ahead.
Yeah, so from -1 to 0, it will be giving 0, and from 0 to 1, it will be giving 1. So for negative value, so the range will be from 0 to 1.
Correct. Yeah, exactly. Right. So this is basically what's going to happen. Right. So now, can someone answer what will happen in this case? So x and y are both between -1 and 1. And what I'm doing is I'm doing some kind of transformation like this, where I'm saying, okay, let's say a is equal to x plus y and b is equal to x minus y. So what is the range of values that a and b will lie in? Or what are the ranges of pairs of values that a and b will lie in? I mean, rather, it's already there. Can you argue why this is the case? So if x and y is between 1 and -1 each, what is the value that x plus y will lie in? Let's see. Can someone
So
say?
like x plus y, so we will take the maximum negative values to calculate the lower bound and maximum positive values to
calculate the upper bound, right? So x plus y will then be -2, 2, right?
Good. Is the rest of the class clear about this?
Yes, sir.
Yeah. And similarly, what about x minus
I
y?
have one more question. Okay, Aritra did answer that
Right.
it is between 0 and 1, if I may. Yeah, is this the smallest interval in this case for the ReLU?
Then -∞ to 1 will also be resulting to 0 to 0, 1.
Yeah, that is I understand that from -1.
Oh, no. The question was that is this the smallest interval? As in,
This is
is the
smallest
interval on the
for the input range -1 to 1.
right? So is this the smallest possible output interval? Because I can always, so for example, I can also say something like this, right? So I can say that I'll go to 0 to 2 instead
Or
of
0 to
saying I'll go
infinity,
to
you could say, yeah. I mean, it's
yeah.
so when you construct abstract transformer, that's also important. The point that I was trying to make.
Right. So this is also technically correct statement in the sense, right? So if x is between -1 to 1, the value of x
Yeah, I
is
get it.
definitely between 0 to 2. But that is, we don't want that. We want actually the smallest interval possible, right?
Yeah. I got the argument. Actually, I was thinking wrong.
Right. So okay,
Does the rest of the
what about
class understand it? I mean, you should be forthcoming with your questions and things too. Yeah, go ahead. Yeah, I think I will rotate. Let me see what the time is now. So, yeah, it's 4:45. You can take 5 more minutes and you can actually ask somebody else this question for the next example.
right x minus y? So
Yeah,
what will happen
it's
with
x
x minus y?
minus
Somebody.
y. I'll go to Vardhan. Can you take a crack? What is the question is what is the interval
That x minus y will have and y for
and
when x and y are between 1 and -1.
some interval and your smallest possible interval that you can think of.
So x and y are just some real numbers between -1 and 1. And I'm asking that, okay, what is an interval within which the value x minus y will always be contained in? And what is the smallest such interval that you can think of?
Anybody else?
Sir, I can try, sir. The maximum value x minus y will take is when x is 1 and y is -1, then the maximum
Right.
value will be 2.
Correct.
And we can argue the similar for the -2 also, when x is -1 and y is +1.
Right.
Yeah, that's
So it'll be,
yeah.
so the interval will be -2 to 2 is what you're saying, right? Yeah. Okay. So that's correct. But now I want to show something very interesting happening in this case. So now I have a very, very interesting question, right? So we are converting xy to ab, where we're saying we're taking pairs of values x comma y, let's say vectors of values x comma y, and sending in to these vectors ab, which is defined as x plus y, x minus y, right? And what we knew about these pair x comma y is that this pair was such that x is between -1 and 1, y is between -1 and 1, right? And now what we have calculated is that, okay, x plus y will be between -2 and 2, x minus y will also be between -2 and 2. And in fact, that those are for x plus y, that is the smallest interval that we can come up with, because it is possible that x plus y is -2. It is possible that x plus y is 2. So you cannot have a smaller interval. Then you'll miss the -2 and the 2 values. Similarly, for x minus y, it is possible that it will be -2. It is possible that it will be 2. So you cannot get a smaller interval without missing some values, right? So now what we're saying is that this a comma b pair is in this kind of a space where a is between -2 and 2 and b is between -2 and 2, right? So my question is all possible pairs of values, so where a is between -2 and 2 and b is between -2 and 2, is all possible pairs of values realizable from an xy such that a is x plus y and b is x minus y? Is that always the case? Is it always the case that if I pick an a from -2 to 2 and one b from -2 to 2, there will be an x and a y each from -1 1 such that a is x plus y and b is x minus y? Is that always the case?
It is not missing out any values, correct? Is that
Right.
the question that you're asking?
So am I saying that do I have extra values here? right?
Yeah, I mean, does it have
yeah.
extra values? Okay, there are two.
Yeah.
Both are relevant questions. It must be
Right. So I think we have already asked the question whether we're missing out any values.
Yeah.
Right?
So you think is this the smallest? Or does it have any extra things? Yeah, that's your
correct.
question.
Exactly. So just to repeat what Sir said. So we've already shown that okay, for any xy, for any x comma y which is in this kind of a place -1 1 cross -1 1, we know that this a comma b will be belong in this -2 2 cross -2 2. Further, we know that we can't make each of these intervals any smaller, right? So we can't, for example, I can't say -1.92 because then I'll miss out something, right? So we cannot make any of these intervals smaller. But my question is it the case that for all a comma b, there exists x comma y? So for all a comma b belongs to, let's call this guy I2, let's call this guy I1. For all a comma b belongs to I2, is it the case that there exists x comma y belong to I1 so that a comma b, a is equal to x plus y, b is equal to x minus y, right? So that is, are we really, having something extra? If this is false, that means that there are some pairs of values a comma b in I2 which don't come from any x, y in I1, right? Which means we've somehow added something extra by doing this kind of transformation. If this is true, then that means it's exact, because then every xy goes to some ab and every ab comes from some xy. But if that's not the case, then that means that there is some ab's in I2 which don't come from an xy, which means we have somehow added something extra. So is that the case? Are there values of ab which are within this range -2 2, which is it's not possible to get from an xy which is within this -1 1 range? Anyone?
So
So
A
that will
and
be
B.
Just a minute. Just a minute. Okay. So who's one at a time? Okay. I'll ask, even if you can't answer this, we only have, the class. I want to end the class off with this question.
Yeah,
So,
exactly. That is what I want.
Yeah, Bijayan.
Yeah, sir. Yeah. Good. So, uh, so the I'm not sure if I got the question correctly. Can you just repeat the question once more?
Yeah. So, are there any ABs?
Repeat the question, Diganta. Repeat the question, and I say that I want to let them think, and you can, don't give the answer out. Okay, let them back think, and then I hope that they will have, or you could send it by email to Diganta.
Yeah. Sure.
Or you.
So I mean, yeah. So the question is just that if A and B are inside this kind of an interval where A is within -2 2, B is within -2 2, is for all possible ABs that are within this thing where A is between -2 2 and B is between -2 2, does there always exist an xy so that x is between -1 1, y is between -1 1, and A is equal to x plus y and B is equal to x minus y? Is that always the case?
No, sir, because one counterexample can be when x equals to 1.5 and y equals to 0.5.
Right. So when x is equal to 1.5, you can't take x equal to 1.5 because
it's 1.5 because it lies between -2 and 2.
No, but x needs to lie between -1 and 1, right?
Sorry, sir. I was talking about the values of. Okay, sir. Sorry, sir.
You
right.
can
I mean, you can either give me.
Yeah. Okay. So counterexample can be a comma b equal to 2 comma 2. So then x comma So yeah.
Yeah. So if it's 2 comma 2, then the only if a is 2, then the only thing possible is x and y both need to be 1, but then b needs to be 0, right?
Yeah.
That's absolutely correct. So notice that this is something very interesting. This is indeed the smallest intervals that we would come up with. We cannot come up with a smaller interval for x1, x plus y. We cannot come up with a small interval for a. We cannot come up with a smaller interval for b. But even with the smallest intervals, we now have something extra, right? So actually, the set of pairs of value x plus y and x minus y can't even be expressed as intervals of this form, right? Why is that the case? That's very easy to see if you draw out a diagram. I'll just say this and end if that's okay with you, sir.
Sure. Yeah, I think some people have classes at 5. Therefore,
Yeah,
just
just
do it and
to
revisit this because this is important. I mean, those situations where just having intervals is
insufficient,
is necessarily, you will lose precision. Yeah.
Right. So let's say that this is my xy plane, and I'm saying that x comma y is between 1 and -1, which means what? That my xy pairs will line some box that looks like this, where this is -1, this is 1, some box like this, right? So when I send it to x plus y, x minus y, what happens, right? So what happens in the AB plane? So what happens in the AB plane is that, this is, let's say, A, this is, let's say, B. This box kind of gets rotated, right? So, your two axis aligned vectors get rotated by 90 degrees. So you end up having this kind of a box, right? So this is visually what this transformation is doing, right? So this box has now gone here. And now what we are saying is that, okay, these corners are actually at -2 and 2, right? So now what we are saying when we're drawing this, when we're calculating this interval is that, okay, this is inside an interval which looks like a box like this. And if you remember, the counter example that somebody came up with was essentially this corner over here, which of course does not, come from the box, right? So this is the smallest possible interval in the sense that if you want your boxes to be axis aligned, which is really what we're doing when we're taking intervals of this form, you cannot shrink this box any smaller because then you'll be cutting off some parts of the actual rotated solid, black box, right? So this is the smallest thing, but even then, all of these guys are going to be extra. So it turns out, so if you remember that what I've been saying is that an abstract domain is a parametric representation of a set. It turns out that if the abstract domain that you have is an interval in which, the kinds of sets that you're tracking is an interval, then this is a transformation in which the result will never be exactly trackable by an interval. So you'll always lose some information, and that will always looks like adding some things extra, right? And this will become very important when we take it up in the next class and we actually look at what happens in an interval, in a neural network when we use an interval domain, right? So I think this is a good point to stop.
I think it's a good point to stop. Yeah.
Yeah,
okay.
I think I've already taken up
think
too
about
much.
These examples, the people that, there was,
I think
then has something here, some micro.
So it's
that's
it's
okay.
like we are applying. Hello.
Go ahead, a question.
So it's like it's like So it's like we are applying a transformation, and then the square we had initially is rotated to some extent, and now we want to get a square covering of that. And the claim is there will always be a part which is outside.
Correct.
Right. Because it's not representative, it's not coverable within this, right?
Okay. I got it.
Yeah. In fact, I mean, there is a really nice formalization of this via something called Galois connections, which I don't plan to talk about for sake of time. But I mean, look up Galois connections if you want to formalize this notion very nicely.
Yeah, I will upload some slides. I have slides that I covered in my software verification course on Galois connection and so on. I can upload those slides and give references and so on. The one thing, okay, I think we are running up because some other people are doing it. And I think one request for Diganta is for you to give me some references, papers, and so on that I can upload, just like I did for ReLUplex and node merging abstraction. So that
that I'll send,
that I will do. So okay, let's so that you're not missing any point. Let's. In the next class, sure, you'll raise the same question so the rest of the class, understands it as well. So, yeah, thank you. Yeah, okay.
Yeah, thanks everyone.